In this video, we will look at rays in Mobius. A ray is a line that starts at a specific location and continues forever in a specified direction. A ray has an origin and a direction. The length of the ray is infinite. You may be wondering how rays differ from vectors. A ray has an origin, so it is fixed in a specific location in space. A vector has no origin, so it can float around in space. A ray has no length, since it is infinite. A vector has a specific length. A ray is a purely mathematical concept. In Mobius, rays are used by various functions to perform operations, but there is no geometric entity for rays. In Mobius, a ray is represented as two lists of three numbers. The first list is the origin of the ray. The second list is a vector specifying the direction of the ray. Note that we said a moment ago that a ray is infinite and that a vector has a fixed length. In this case, a vector is used only to define the direction of the ray, not the length. The actual length of the vector is ignored. Later, we will see that it is useful to be able to set the length for visualization purposes. Let's look at some functions that use rays. We will start with the primary functions, and then look at the inline functions. The calculate.ray function can be used to calculate rays from edges or faces in the model. Given an edge, the function will return a ray aligned along the edge. The ray origin will be at the start vertex of the edge. The ray direction will be a vector from the first vertex to the second vertex. Given a wire or polyline, the function will extract all the edges and return a list of rays. Given an polygon, the function will return a ray perpendicular to the polygon. The ray origin will be at the centroid of the polygon. The ray direction will be a vector perpendicular to the polygon. The function is overloaded. If you pass in a list of polygons, it will return a list of rays. The modify.rotate function can be used to rotate geometric entities around a ray. The direction of rotation will be clockwise when looking in the direction of the ray. The modify.mirror function can be used to mirror geometric entities in a plane. However, the function is overloaded and will also accept a ray instead of a plane. Given a ray, the function will generate a plane that passes through the ray origin and that is perpendicular to the ray. Various other functions use rays. In most cases, the length of the vector used to define the ray direction has no impact. For example, the intersect.rayFace function calculates the intersection between a ray and a face. The function assumes that the ray is infinite in length, so the length of the direction vector has no impact on this function. Now let's look at some of the inline functions. A series of inline functions are available for working with rays. The raymake will generate a ray with a direction vector of the specified length. If no length is passed in, then the vector length is not modified. There are also functions for moving and rotating rays. The rayMove function moves that ray using a vector. The ray is moved relative to the axes of the global coordinate system. The rayRotate function rotates one ray around another ray. The rayLocalMove function moves that ray in the direction that the ray is pointing. A negative distance can be specified, in which case the ray will move backwards. The inline functions for rays are all overloaded. If you pass in a list, it will reapply the function to each item in the list. So in this example, there are 4 rays but only one distance. The function will move each of the 4 rays by the same distance. You could also pass in 1 ray and 4 distances. In that case, the function would move the same ray 4 times, each time a different distance. Another possibility is to pass in 4 rays and 4 distances. In this case, the function will assume that you are trying to do a one-to-one matching. It will move each ray by each distance. Note that is the list of rays and list of distances at different lengths, the function will give up and throw an error. In such a case, the function cannot figure out what you are trying to do. The rays that your procedures are using are not geometric entities. As such, they are not visible in the viewer. However, sometimes it is useful to be able to see the rays. It can help to better understand what is happening and to verify that the rays are actually in the correct location. The visualize.ray function can be used. The function will generate some polylines, consisting of the ray line and an arrowhead. The ray line starts at the origin, and is equal in length to the length of the direction vector. The second argument is the scale factor for the arrowhead. It allows you to increase or decrease the size of the arrowhead. The scale factor does not affect the ray length. Note that the visualize.ray function does not generate a ray entity. It only generates some standard polylines. The polylines that it generates cannot be used in functions that are expecting a ray. Lastly, the visualize.ray function is overloaded. If you pass in a list of rays, it will visualize all the rays.